Physics can be a headache, especially when we start talking about real, reactive, and apparent power. You see this triangle in every BTech and degree textbook, but why does it matter to an electrician or an engineer? I'm Prosi, a master's electronics engineer, and today I'm going to use the Coca-Cola analogy to make this click for you forever. By the end of this video, you won't just know the formula, you'll understand the physics. Imagine you buy a glass of Coca-Cola. This is the Coca-Cola itself. This is what you actually drink. In electrical terms, this is what. It's the energy that actually does the work, turning a motor or heating a kettle. The form that you see on top here is reactive power, Q. This is the head on the Coca-Cola. You can't drink it, but it's there. In a circuit, this is volt amps reactive, VAR. It's the energy used to create magnetic fields in motors or transformers. It doesn't do any work, but we need it for the system to function. As you see, the whole glass is apparent power, S. This is the total volume, the liquid plus the foam. This is VAR, volt amps. This is what the utility company has to deliver to your house, and it determines the size of your cables. The goal of a good engineer is we want as much Coca-Cola as possible and only a little bit of foam. That's power factor correction. Now, how do we calculate it? We use Pythagoras Theorem. This is the Pythagoras Theorem. We can tell that this triangle has 3 sides on it, and we are going to use the Pythagoras Theorem for right angles. Okay? Think of the triangle. So we have the horizontal line, P, which is this one, vertical line, Q. So P will be your hardworking watts, and your Q will be your form, the reactive. And then the hypotenuse will be your total glass. If the angle between P and S is too big, you're paying for a lot of foam and not getting enough Coca-Cola. As a master's engineer, it looks that this angle, or I look at this angle and see efficiency. The practical part of it is, in the domestic world, we care about this because if your power factor is bad, your cables get hot and your efficiency drops. As a master's engineer, the shortcut isn't just memorizing the letters. It's about understanding the visual logic so you never have to look at a textbook again. Here is the deep explanation of the engineer's shortcut for the power triangle. So S squared is P squared plus Q squared. The alphabetical shortcut. If you forget which letter goes where, look at the alphabet. P comes first. So P comes first, which is the horizontal base, and it's always in watts. It's the foundation. Q comes next. It's the vertical part of the triangle, which is the height, and it's the reactive power, and it's turning up at 90 degrees. S is the result. That's the hypotenuse. It's the sum of the 2 sides. The right angle logic is the Pythagoras. So this right angle you see here is the logic we use for Pythagoras. Because the relationship between real power, which is P, and reactive power is exactly 90 degrees out of phase, they always form a perfect right-angled triangle. So P in watts, Q in VAR, that's the imaginary or magnetic work, and the S, which is the total or your apparent power. So the shortcut would be easier. Instead of always writing S squared is P squared plus Q squared, engineers often just use the square root immediately. So they just say S is equal to square root of P squared plus Q squared. If you have a calculator, just square the two sides, add them, and hit the square root button. That's your total apparent power. So the power factor trick, the most important shortcut for an engineer is the cos phi idea. So power factor is P, which is your real power, divided by the total. Think of it as your efficiency score. If the result is 1, you are 100% efficient. All Coca-Cola, no foam. If the result is 0.5, you are only 50% efficient. So you half your energy is being wasted as foam. I hope you get what I'm trying to say. So half of your energy is being wasted as foam if the result is 0.5. So the apparent power is what determines the size of the wire we install in a house. Even if the real power is low, the reactive power Q is high, the total current S will be huge. Okay? The result, you need thicker, more expensive cables. Here are two perfect practical problems for us. Okay? Let's go through them. So we have a scenario. Okay? So scenario. So I'm going to say you're installing a motor for a large gate. The motor plate says it uses 800 watts. That's real power. And creates 600 VAR, which is your reactive power, due to its internal magnets. Internal magnets. What is the apparent power? Question: what is the apparent power, which is our S, that the cable actually has to carry? So what do we look at there? So it's asking for apparent power. So we saw that S is equal to the square root of P squared plus Q squared. So we already have 800 as our real power, and we have 600 as our reactive power. So S will equal to the square root of 800 squared plus 600 squared. Okay, this will give us 64,0,123 plus 36,0,0,0. Okay, this will give us the square root of, get your calculators and sum it out, will be 1,000,000, which will give us the square root of 1,000,000 will be 1,000, or 1 kVA. Okay, you note that how the cable has to carry 1,000 VA even though the motor only does 800. So this is our answer that we've got. It's carrying 1,000, but we just had in our question that the motor only does 800 watts of work. So that extra 200 is the foam we talked about. So now that we've got 1,000, look at the 800. So 800 watts, 1,000 VA. Okay, so it will still require you to understand the concept of the Coca-Cola so that you don't get anything wasted. Okay, so notice that how the cable has to carry 1000 VA even though the motor only requires or does 800 watts of work. That extra 200 is the form we talked about. Okay, so let's go to another problem. Okay, so problem 2, we have a scenario. A workshop has a total apparent power. A workshop has a total, it has a total apparent power S of 5 kVA and a real power P of 4 kW. The question is, what's the power factor and is it efficient? What is the power factor and is it efficient? So calculation, we already know that power factor from our previous notes, that power factor is P over S. P being, in this case, we have real power P as 4, and then we have apparent power as 5. So this will give us P as 4 over 5, which will give us 0.8 or 80%. Okay, so in engineering 0.8 is okay, but we want to get closer to 0.95. As an engineer, I would look at this and suggest adding capacitors to shrink that reactive power and save the client money on their bill. Okay, so now that we've got 80% in engineering, yeah, it will be okay, but we want to get closer to 0.95. Okay, so what we could do, we would suggest adding capacitors to shrink the reactive power and save the client money on their bill. I hope you're understanding what we're trying to explain. So thank you so much. I look forward to giving you more. Don't forget to subscribe to our channel and more videos. I'm going to link up a link for you to book if you need extra lessons. Thank you so much. Ciao.